One of the most annoying things I hear as a developer is you don't need to know any math to write code. You just need to know how to code. Computer science as a field was invented by mathematicians and cryptographers for a reason. There's a ton of math involved, even if it's usually abstracted away from you by some library. But if you want to be someone who actually knows how code works under the hood, so that your skills are valuable in the market, then you gotta know the math. Of course, the question is, which math? So I've compiled some of our most need-to-know math videos from the BootDev course platform, and today we're releasing them together here in this video for free. So enjoy. We'll start with the simpler stuff, like binary factorials and floor division, and we'll work our way up to some of the more advanced stuff like vectors and randomness. So without further delay, let's understand binary numbers. Most people have heard that binary is the language of computers, and they assume that means it's like some kind of confusing foreign language. But it's actually so much more simple than that. It's actually the simplest number system outside of unary, which, unary is actually just counting on your fingers and toes. But before we jump into binary, let's talk a little bit about the number system that you're already familiar with, decimal, or base 10. And it's called base 10 because there's 10 symbols in the number system. These symbols. So this circle represents 0 things or nothing, whereas this symbol that looks like a line represents a single thing, 1 thing. This other symbol represents 2 things. This symbol represents 3 things, and so on. So representing the numbers 0 through 9 is really easy in decimal because we have 1 symbol per number. But like all number systems, it gets a little more complicated when we want to represent numbers that are larger than the total number of symbols that we have. So how do we represent 10 things? Well, we introduce a new spot. We call it the tens place. So we have the ones place where the symbol in that spot just represents that number itself. The tens place represents 10 times the value of the symbol found in that spot. So the symbols 1 and 0 represent 0 single things and 1 10 thing. Let's use another example, it might be more obvious. The symbols 2, 5, of course, represent the number 25, but it's because there are 5 things in the 1 spot and 2 things in the 10 spot. So we take 2, multiply it by 10, and add that to 5. Now, binary works the exact same way, but it's actually just a little simpler. Instead of 10 symbols, we only have 2 symbols, 0 and 1. And instead of ones, tens, and hundreds places, we have 1s, 2s, and 4s places. So let's just count from 0 to 8 in binary, and I think it'll start to make sense. 0 is just 0. 1 is just 1. Now, up till now, this is exactly the same as decimal, but we've run out of symbols. So now we add a 2's place. And to write the number 2 in binary, we put a 1 in the 2's place, and then we leave the 1's place as 0, just like we would have with the number 10 in decimal. So 1, 0 represents the number 2. Then to count up 1 more, we just add 1 to the 1's place. So 1, 1 is 3. Now we need another place. So let's add a 4's place. 1, 0, 0 is 4. 1, 0, 1 is 5. Now we can reuse the 2's place. So 1, 1, 0 is 6. And 1, 1, 1 is 7. Finally, the 9th number, 8, well, we need an 8's place. So 1, 0, 0, 0 is 8. All right, one last example. Let's take a big binary number and break down what it is. So let's take 1, 1, 0, 1, 0, 0, 0, 1. First, let's just visually mark what all the places are. We've got 1s, 2s, 4s, 8s, 16s, 32s, 64s, and a 1/28ths place. So we have 1, 128, 1, 64, no 32s, 1, 16, no 8s, 4s, or 2s, and a single 1. And then if we add all that up, we get 209. What is this equal to? If you're a programmer and you let your eyes deceive you, you might think 5 exclamation point means not 5. But no, it's actually a math thing. It's a factorial. A factorial is the product, meaning the multiplication result, of all the positive integers less than or equal to the given number. So, for example, 1 factorial is just 1. 2 factorial is the same as 2 times 1, which is just 2. 3 factorial is the same as 3 times 2 times 1, which is 6. 4 factorial is the same as 4 times 3 times 2 times 1, which is 24. And 5 factorial is the same as 24 times 5, right? Think about it. We already did all the other ones. So 5 factorial is 120. Now, there's also a special case. 0 factorial is equal to 1. It makes a bunch of math work out nicely, so that's just how it works. Now, again, when it comes to programming in Python, the exclamation mark is not a factorial operator. You can't write 5 exclamation point in code and expect to get a function that calculates factorial. You need to write it manually. So let's go ahead and write one. We can define a new function called factorial that takes the number as input. We'll just call it n. Then we keep track of a product. We'll start at 1 because remember, both 0 and 1 factorial are 1, so that makes sense. And then for I in range 2 to n plus 1. Or in other words, for every number from 2 up to n, because n plus 1 is exclusive, we'll multiply the product by that number. And then when we're done, we return the product. Now, let's run our function and see how insanely fast factorials grow as n gets bigger. The factorial of 5 is 120. Factorial of 6 is 720. Remember, it's just 120 times 6 now. Factorial of 7, 5040. Factorial of 10, 3,628,800. And factorial of 20 is, I can't read that. There's 18 digits after the 2. So they get really big really fast. They actually grow even faster than exponentiation. For example, 20 factorial is astronomically larger than 2 to the 20th because the base keeps increasing with every multiplication. Exponents are super easy. Really, do not let the complicated, confusing name get to you. An exponent is just a mathematical operator that multiplies a number by itself a certain number of times. But before we go deeper into that, let's just review some even more basic math to make sure that we're on the same page. As you know, 2 times 2 is 4. We're saying that we have 2 2s. Similarly, 3 times 3 is 9. Again, we have 3 3s. It's really 3 plus 3 plus 3. This relationship between multiplying and adding is very similar between exponents and multiplication. 2 raised to the power of 3 just means 2 multiplied by itself 3 times. So 2 raised to the power of 3 is 2 times 2 times 2, which is 8. 2 raised to the power of 4 is just 2 times 2 times 2 times 2. Which is 16. And 3 raised to the power of 5 is just 3 times 3 times 3 times 3 times 3, which is 243. So the results of exponentiation actually get really big really quickly. 2 to the 6th is twice as big as 2 to the 5th. Okay, now that you get that, let's go over just a couple of special cases. Anything raised to the power of 1 is just itself. So 4 raised to the 1 is 4 and 5 raised to the 1 is 5. This one's pretty obvious. This one's a little weird though. Anything raised to the power of 0 is actually just 1. So 5 raised to the 0, 1. 7 raised to the 0, 1. So how do we do this in code? We obviously can't use superscripts because code is just plain text. We don't have that kind of fancy formatting in our code files. Well, Python is actually one of the few languages that has built-in support for exponentiation in the language itself. And the exponentiation operator is just star star. It's like 2 multiplication symbols. So 2 to the 3rd in Python can be expressed as 2 star star 3, which will evaluate to 8, or 3 star star 3, which evaluates to 27, 3 to the 3rd. A logarithm is the inverse operation of exponentiation, basically a backwards exponent. So we know that 2 to the 3rd power, 2 times 2 times 2, is 8. And 2 to the 4th power, or 2 with a for exponent is 2 times 2 times 2 times 2, which is 16. A logarithm is when the thing that we are calculating isn't the result of exponentiation, it's the exponent itself. In these examples, the 3 and the 4. For example, log base 2 of 8 is 3. Just like 2 raised to the 3 is 8. Log base 2 of 16 is 4, and log base 2 of 32 is 5. Now, in mathematical notation, log base 2, the base is typically written in subscript, of 16 equals 4. That's how we'd read it in English. And what log base 2 of 16 really means is, what I recommend you kind of think of it in your head as, is what's the power that I need to raise 2 to get the result of 16. And of course, in this case, the answer is 4. Now, the base doesn't have to be 2. In programming, it's really common for the base to be 2 because we work in binary. But we could also take log base 10 of 1000. And what do you think that is? Remember, the question is, what's the power that I need to raise 10 to get a result of 1000? Well, the answer is 3, because 10 to the third is 1000. Let's take a look at a bunch more examples. Log base 2 of 2 is 1. Log base 2 of 4 is 2. Log base 2 of 8 is 3. Log base 2 of 16 is 4. Log base 2 of 32 is 5. You get the idea. Log base 10 of 10 is 1. Log base 10 of 100 is 2. Log base 10 of 1000 is 3. And log base 10 of 10,000 is 4. So it's important to understand that exponents grow very quickly. 2 to the 2 is 4. 2 to the 3 is 8. 2 to the 4 is 16, 2 to the 5 is 32, 2 to the 20th is 1,048,576. On the other hand, logarithms grow very slowly. Log base 2 of 2 is 1, log base 2 of 4 is 2, log base 2 of 8 is 3, log base 2 of 1,048,576 is just 20. And even more crazy, I'm gonna have to read this one off, log base 2 of 1,099,511,627,776 is 40. Now, because logarithms grow so slowly, they're really useful when it comes to coding and computer science. When we write a program that gets slower in exponential time, that means it's going to get really slow as its input size grows. But if our program only gets slower at a logarithmic rate as its input size grows, it's going to be a really fast program. Floor division is just like regular division, but there's a slight twist. The remainder is ignored or truncated or dropped, at least with positive numbers. Let's go over a few examples, but first with regular division. 6 divided by 3 is 2. 8 divided by 2 is 4, and 6 divided by 4 is 1.5, because 4 goes into 6 one whole time, and then half a time more, right? Because it goes into 6 once, then we're left with a remainder of 2, and 2 divided by 4 is 0.5. So in all of these examples, we divided one integer by another integer, and we were actually left with, at least in the case of the last example, a fractional part, which isn't an integer. In Python, it's called a float, or in a language like C, it might be called a double. So what is floor division? Floor division is just like regular division, but after the division operator, we have one more step. We floor the result. And floor really just means to always round down, no matter what the fractional part actually is. So while 6.8 rounded might round up to 7, 6.8 floored will still be floored down to 6. And flooring a negative number, like negative 5.6, actually results in negative 6, because negative 6 is less than negative 5. And in Python, when we want to do floor division, there's actually a special operator for it. The regular division operator is just a single slash, but the floor operator is actually 2 slashes. So 6 floor divided by 3 is still 2, just like 6 divided by 3 is 2, but 7 floor divided by 3 is also 2, whereas 7 regular divided by 3 would be 2.33333. So to use our original example, 6 floor divided by 4 isn't 1.5, it's just 1. Whereas 9 floor divided by 4 is just 2. And that's because 4 goes into 9 a full 2 times, and then the fraction is dropped. People People always talk about below average height or above average intelligence, but that's usually the wrong way to look at it. Now, before I explain that, let's talk about what average even means. It's also called the mean, and it's just the sum of a group of numbers divided by the count of those numbers, how many numbers there are. For example, say I have the numbers 0, 5, 3, and 2. To calculate the average, I add them up, which is 10, and the total count of numbers, how many I have, is 4. So 10 divided by 4 is 2.5. And here's the thing, averages have a problem. In most real world scenarios, they get massively skewed by outliers. To show you what I mean, let's add a 75 to our example from before. Now the sum is 85, the count is 5, and 85 divided by 5 is 17. So the mean, or the average, shoots up from 2.5 to 17. But the interesting thing is, there are no numbers in our set that are really close to 17. 4 of them are much lower and 1 of them is much higher. So if you're trying to find a number that represents the typical number in a group, medians tend to be better than means or averages. A median is the middle value after you sort the group into an ordered list. It ignores how big the other numbers are and just picks the one in the center. So using our same example, first we sort the list, and then we just take the middle number. In this case is 3. So the median is 3. And if you have an even count of numbers, you just average the 2 middle ones. For example, if the numbers are 0, 2, 3, and 5, we just take the mean of 2 and 3, which is 2.5, and that's the median. Now, medians are a bit more annoying to calculate because you have to actually sort the list instead of just doing some simple arithmetic, but it is usually what you want when you're looking for a representative number. Do you know the answer to this problem? Now, at first, you might think it's 3.5 because 7 divided by 2 is 3.5, right? But it's not. In programming, this symbol, unlike the slash symbol, is a modulo operator. It's like division, but not quite the same. 7 mod 2 is actually just 1 because this operator returns the remainder after the division. So 2 goes into 7 3 times, sure, but we don't actually care about that. 1 is left over after the division, so the answer is 1. Modulo doesn't actually care about the results of the division, it cares about the remainder. Okay, so what's 8 mod 3? Well, 3 goes into 8 twice, which is 6, and then 2 is left over, so it's 2. And how about 11 mod 3? 3 goes into 11 3 times, which is 9, and 11 minus 9 is 2 again, so still 2. Modulos are useful for all sorts of reasons, but a simple one is finding even numbers. You can check if a number can be divided evenly by another number by checking if the result of modulo is 0. So unlike a lot of the goofy is even functions that you've seen out there, x mod 2 equals 0 is a great way to check if a number is even. How do computers generate random numbers? It's something most developers take for granted. You just call something like math.random and move on with your day. But how does that math.random function actually work? Like, if you didn't have a standard library, how would you get a random number? How do you write a program that does something differently every time that it's run? I mean, you can write a bunch of complicated math to calculate a number that looks random, but if the calculation's always the same, you will get the same result every single time. The answer is we don't generate randomness in a vacuum. Instead, those built-in randomness libraries actually reach out to the operating system for a source of entropy, or a source of randomness. The operating system is responsible for gathering the entropy, and usually it does it by sampling from unpredictable real-world events. Things like mouse movement timings, keyboard timings, disk I/O latencies, even electrical noise in the CPU, stuff that changes constantly and can't be easily guessed. Now, once the OS has that noisy input, it can process it, typically through a cryptographic hash function, to generate some random bytes. And from there, those bytes can be mapped to whatever range you actually need, say a random number between 1 and 10. The critical part is making sure that the entropy source, the seed, is really unpredictable. That's especially important when you're doing something security related, like generating private keys. In those cases, you absolutely need to make sure that you're using a cryptographically secure randomness function. Now, most modern programming languages have libraries for this, and they'll tell you in the docs whether a randomness function is cryptographically secure or not. If it's not, it probably just uses something like the current timestamp as a seed, and that's fine for stuff like generating loot drops in a game, but for anything where real security matters, you need a better source of entropy.
Vectors are lists of numbers that represent points in space, direction and distance, or magnitude, from the origin.
It's a mathematical term, a quantity represented by an arrow with both direction and magnitude.
When it comes to things like semantic word embeddings, a vector's direction and distance from the origin represent the meaning of a word. Imagine a giant 2D space where this area has words like happy, joyful, and excited clustered together, while another area has words like sad, depressed, and angry. Similar words have vectors that are closer together in that space, while dissimilar words have vectors that are further apart. Let's look at two vectors, 0.5, negative 0.2, 0.8, 0.1, 0.9, negative 0.3. We can add vectors element by element, so 0.5 from the first vector plus 0.1 from the second vector gives us 0.6. Negative 0.2 and 0.9 gives 0.7. And finally, 0.8 and negative 0.3 gives 0.5. This is vector addition, and in the context of semantic embeddings, it means this concept mixed with that concept. For example, a vector for family-friendly movie plus a vector for horror movie will give us something like a family-friendly horror movie. Vector subtraction removes concepts. It's like saying, I want this, but not that. So take 0.5, negative 0.2, 0.8 minus 0.1, 0.9, negative 0.3, and you get 0.4, negative 1.1, 1.1. For example, horror movie minus bear movie will give us a vector representing something like a horror movie without bears.